So hi everyone, I'm MehdyLefkir. I'm a second-year PhD student at the University of Leicester. And today I'm going to talk about time series analysis, but more on the aperiodic domain, so essentially stochastic variability from AGN. Yes, this one. Yeah, great. So first I will motivate basically my work, which is essentially trying to understand the peculiar or let's say simple behavior of this kind of time series. So here is an example of essentially nearly all of the XMM observations, so light curves of a Cepheid-1 galaxy, which is called NGC 4051. And you can see random, completely stochastic variations in the light curve. And so the idea is, what's the physical origin of this? And if we want to try to answer this question, we can also try to figure out what are the correlations and delays between, for instance, two energy bands, so either in X-rays or with UV and optical. And this basically will help us understand the structure and essentially the physical processes occurring at the center of active galaxies. And so usually what is done is Fourier analysis, so estimating the power spectrum using periodograms. And in the very, very first, or let's say zeroth order, we find that the power spectrum is a broken power law or bending power law, where the break or bend frequency is related to the mass of the black hole. So the faster the object will vary, the more probable it will be a smaller mass black hole. And so here you've got essentially one of the first results of this kind of analysis. There are recent, let's say, developments. So essentially the mass, it's not just the mass, it's also basically luminosity and absorption and other things. But for this work, we will just focus on the mass and bend time scale. And so if you've looked at the list of essentially observatories that you can see here, essentially XMM and Swift, XMM and ASCA provide, let's say, fairly regularly sampled time series. But if you look at Swift or RXC like curves, then you won't find lots of them which are evenly sampled. So we need a method which can cope with gaps, arbitrary sample, time series, uncertainties on measurements, because you may know that the periodogram doesn't account for error bars. And in the case of AGN, leakage and aliasing, because we can't observe them for, let's say, millions of years or even thousands of years. So we have only got like a snapshot of basically the behavior of these sources. And so to tackle these issues, we are going to work in the time domain. So if you're an expert on Gaussian processes, then you can go to sleep for the next 5 minutes. If not, then I will give you, I promise, a very short introduction on Gaussian processes and why it's very useful and it's a very impressive method. So to put it very simply, it's a nice way and easy way to interpolate points, assuming that you have Gaussian data. And it's fully described because it's a multivariate Gaussian distribution. It's fully described by its mean and covariance function, or covariance or auto-covariance function in the case of time series. And this covariance function is extremely important because it will basically control how smooth and how your realizations and by extent your time series will look like. So if you've looked at time series from AGN, you know that basically this this left panel is not realistic. In X-rays, you don't see light curves which are as this smooth, but maybe closer to the one on the right, which is with an exponential covariance function. So maybe if we have a good covariance function, maybe we can figure out how this source is variable. So the idea how to do regression is essentially to assume a model first. So this is a top plot, which is essentially a Gaussian process with the covariance functions that you chose. And this will control your the smoothness of your realizations. And then you've got your data that you've obtained from a telescope or something else. And these are essentially the red points. And the idea is that we want to find a process which can reproduce this data, but also predict some new data. And so the idea, the basically the operation that we do is conditioning. So it's conditioning in terms of probability. We find the distribution of the process, which can basically explain this data, assuming our model. And the idea is that we can also derive the likelihood function, which will give us essentially a number which will tell, is this the best covariance function with this kind of parameters? And so you probably see where I'm going. If you know that basically the power spectrum and the autocovariance functions are just Fourier pairs. And this is what was done 10 years ago by Lance Miller and Abdou Zogby, where they essentially wrote a model in the Fourier domain, took the first Fourier transform, and then did Gaussian process regression. And then you get essentially a likelihood is the same way and optimize or sample from the posterior to get your model. And so, as I said, this is essentially the standard way, but there is one big issue here, is that this likelihood is extremely, extremely expensive to compute. It scales that as n cubed, where n is your number of data points, and you have to store a matrix, which is n by n. So if n is more than 1,000, then you can't work on the CPU, you have to use a GPU, and even then, it's going to be a bit slow. So thankfully, a few years back, people started to implement scalable methods, such as the dump random walk or the more general continuous autoregressive moving average process, which has a fixed power spectrum, which is like Lorentzian, so 1 over I squared. And a bit more recent, the célérité process, which is, again, another kind of Gaussian process, where you've got a power spectrum, which is 1 over F4. But that's a good way, because we can find essentially likelihoods and interpolations with a faster and efficient method. But in terms of modeling, it's a bit too restrictive, because we want essentially to infer the bend and the slopes of this model. And so what we want instead is a model like this one. So where you've got a bend and basically two slopes, alpha 1 and alpha 2. And the solution to essentially use this kind of model in a Gaussian regression framework is to approximate this model with the sum of célérité basis functions. So essentially, we'll use célérité, which is a very fast and efficient algorithm, to approximate these functions. So let's take J functions, so 20, for instance. I usually use 20, and compute the likelihood. And it's incredibly fast. So here you've got a benchmark with the likelihood evaluation time as a function of number of points. And the black line is essentially the standard Gaussian process regression, where you take the Fourier transform of your model, of your power spectrum, to get your autocovariance function and do regression. And it's essentially very slow, of the order of a second when you've got 1,000 data points. But if you use célérité with, let's say, the Python implementation, it's faster. And I wrote a Julia code, which essentially does everything, but it's even faster. So with this, we can estimate the power spectrum of any time series, as long as we have a realistic power spectrum model. Okay, so this figure will be very hard to explain, so I won't bother to explain it to you, because it's essentially a Bayesian way of checking that all of what I've explained to you is working. So essentially, from selecting a model to inferring the parameters of this model. And it's called simulation-based calibration. And the idea is basically to draw priors. So essentially say, oh, my slope is something, my bend is something, simulate lots and lots of time series, and then try to recover this parameter and compare them to the true one. And the way it's done, it's basically comparing posterior distributions and saying, have we got an overestimation? Have we got, let's say, an under dispersion in your posterior distribution? So meaning, can we trust zero bars and these kind of things? And what we find is that the bend frequency and the high frequency slope are fine, but the low frequency slope is kind of overestimated. But is this an issue? The answer is probably not. Thanks. And the reason is because you've got a duration, let's say an observation of 10 years, a 10 years long observation, and your band is at a time scale of 9 years. There is probably no chance to constrain the low frequency slope because you've got only 1 year, well, not 1 year, but a very tiny amount of data representing these long time scales. So what we suggest is that if the band is, let's say, close to the duration of the observation, then maybe you won't need to trust your low frequency slope, but you can trust at least the value of the band and the high frequency slope. Okay, so I said we have to assume Gaussian data. If you've worked with X-ray light curves, then you know that it's probably not Gaussian at all, but more log normal. So the way to treat this is essentially to take the log of your data to make it Gaussian, and now you can use it in the Gaussian process regression. We assume stationarity. This may not be true, but we have to work with it. In case we are we suspect non-stationarity, we can split the observation and just study parts of it. And the last part is that, of course, it's sampled from a process and then rebinned. So this is more complex than just taking points of an observation. It's not like sampling, it's binning, sampling. So it's a bit different. So first, I want to show you an application. So this is the light curve of Kilian 564, a bright Cepheid-1 galaxy, our line Cepheid-1 galaxy, observed with XMM. So we've got 12 epochs. And at the bottom, you've got the Swift light curve. So in light blue, overlapped with essentially all the segments of XMM. And you can see that it's extremely, extremely irregular, but we can work with it. And so you probably guessed what I did is that I inferred the power spectrum of this AGN. And I took this one only for one reason, is that this is a unique source presenting two bands in its power spectrum. And this was observed a long time ago using RXT, ASCA, and XMM observation by Ian McCarty. And we retrieve exactly the same results using this method. Probably not as fast as fast Fourier transform methods, but at least reliable in terms of errors and posterior distributions. We've compared it with a single bending power law, and we find a base factor of the order of 1 million. So if you've never used base factor, it just means that it's extremely certain that it's a double bending power law, and there is no chance that it's a single bending power law. And you've probably noticed the steep part, which is essentially changing the basis function to a steeper basis function, enabling power spectra which are as steep as f to the -6, which is a huge progress for this kind of object, which has a slope of nearly 4.2, which is one of the steepest power spectra for AGN. Okay, so now I will move to the work in progress section of this talk, which is trying to infer the power spectrum of lots and lots of unobscured AGN. These are only using Swift, and this picture look really like the ones that I showed you before. So let's just compare it. So here I've added this, I would say, fake point because I didn't make any measurement. It's Cygnus X1, and all of our AGN of interest are located in the upper plane. So what we find is that it's, let's say, fairly similar, but needs lots of work. So I will continue this in, let's say, the next year of the PhD. And so here are the conclusions. So we've got a method to estimate the power spectrum of AGN. It's validated and tested with simulations, and it seems to be reliable, but more importantly, scalable on large data sets. So you don't have to wait for 5 days to analyze one simulation using a GPU. You can use a CPU. And it's got Julia and Python implementations. And I'm currently writing the Stingray implementation so that it's available to everyone, or at least to all Stingray users. And the paper describing this method is currently under internal review, and next steps are essentially improving work and possibly working on other wavelengths and reverberation. Thank you all for your attention.
Thank you, Mehdi. Time for questions. So I'll be the first one to ask for those, or is there, for those who are not that familiar with the theoretical background,
Yes.
what makes your method superior to the others? So it's impressive how well the results are reproduced. Is there anything why we should switch to your method?
Well, first, because it's dealing with irregular sampling. So if you take the Fourier transform, the discrete Fourier transform, you have to assume essentially an even grid of frequency of time, even grid of points in your time series. And the other thing that is very critical in case of AGN is leakage and aliasing, because you've got your essentially long-term variability that you have to model. And this is usually done by detrending your light curve, so making sure that the first and the last points are, let's say, similar. Otherwise, you can have like a time series which starts from here and goes down, but still has some variability. And this adds power to your power spectrum, and this biases all your estimates and everything.
Thank you.
I am Sudeep. I have a question as to, can you flip the process the other way around? For example, generating fake light curve from Fourier signatures. If you do that, would it be, for example, better than Timur-Konning method or something like that?
What do you mean by flipping the process?
So if you have, let's say, a double break signature like you showed, can you generate fake light curve from that?
You mean does it generate fake time series? Oh yeah. Well, that's essentially what I did to test this.
Would that provide advantages over traditional methods like Timur-Konning, which essentially uses the Fourier spectrum?
The thing is, Timmer and Koenig and this method are, well, not this method. Drawing sample from the GP and Timmer and Koenig, it's exactly the same thing. As long as you're simulating longer and with a finer sampling with your Timmer and Koenig, there is no difference, because essentially Timmer and Koenig is just an FFT, a parallelogram-based method. So leakage and aliasing are also critical when you're using it.
Thank you.
Anything online? So we would have time for one more question from the room. If not, let's thank Mehdi again.